Hello, everyone. Let's get started. Welcome to day 2 of Code Astro. Wow, there's some enthusiasm. Very good. Uh, this will get me through the day. All right. So we got a lot to cover today. It's a busy day. But before we get started, just a few reminders. We have the anonymous feedback form. If you have anything you want to give us feedback on, even if just things are going great, please fill out the form. Um, just a reminder about how to doing group work for activities. For the first couple of days, we encourage you to try out this pair programming thing. It may not be something you're used to, but it is. We think it's useful. It is used in industry, especially when people are trying to solve a problem together. So just remember that one person is kind of the driver who is typing the code, but is not responsible for like thinking. Right? They're just typing the code. They're like, just tell me what to do. And then the other person is the navigator who watches what gets typed and provides direction. Oh, you should write this next or write this next kind of thing. The driver thinks more about having the right syntax or where to even click on the screen. The navigator thinks more of a big picture about like, what is the next line we should be writing? What is the block of code we should be doing? Encourage you to switch back and forth. That way, you both have opportunities to be a driver and navigator. And for folks on Zoom, use your screen shares to do this. Okay. And then just remember how to ask questions. Please ask questions often. For folks on Zoom, you can ask questions in the chat box. We're asking people not to unmute unless you're called upon. For Piazza, that's our preferred place people can ask questions. There's an anonymous option. Other people can see your questions. So there's probably, if you have a question, you're probably not the only person that has that question. So posting that question on Piazza, helps more than just yourself. And then you can also ask questions on Discord. This is the best way to communicate with your fellow participants. But you can also ask questions in the Ask Questions channel or in your group channel. You can ask your TA questions, things like that. Just remind folks the goals of the workshop. By the end of the workshop, you'll be able to use the language of software development, develop and release an open source astronomy package, and write code that follows the best practices of software development. For today, there's a zeros go, which is understand what is Gitflow and using Gitflow in your projects, especially if we're working with multiple people in your group. And then reason about Git to understand how to use it for version control to understand how to use it to version control your code, and then to also interactively debug your code using breakpoints and not rely on print statements. And then for the project goal today, is you really want to get a feature working and committed to GitHub. That's like the core of your package. You can be like, but we just started this workshop. Why do I need to be finished with my package? It's because for the rest of the workshop, we'll be adding a lot of scaffolding to your package. All the other things that a package has, such as documentation, tests, various tools, things you need to do to package up your package to be released on something like pip. So you'll be busy doing all of that later this week. So get at least something working that you can be like, this is my package. It does even if it just does one thing, there's one function. It is maybe not everything you envision in your grand schemes, but have something. Because we'll be adding even more things beyond just like working on your package, like core code after today. For example, from yesterday, we talked about having this package that plots the galactic orbits of stars in the Milky Way. For that example, maybe today we'll be continuing to working on the core functionality we sketched out yesterday so that we can produce a single plot of likely galactic orbits given a single star's Gaia ID. So like we're going to plot a single star's trajectory in our galaxy, and that's what we determined is all we're going to do. Just a reminder on optional lessons today. We have 2 optional lessons. We have one on parallel programming and one on AstroPy. Both are just kind of like talking about the best practices of how to use both in your software development packages. Before we get started, make sure you have the latest version of Code Astro. I think Chai just updated the parallelism lesson for later today. So if you go, Sarah showed you 2 options. This is one of the options. You use go to your Code Astro folder. You can do a git stash, a git pull, and a git stash pop, and that will hopefully update you to the latest version and include all of your changes. Some other announcements. We're going to do a workshop photo at the end of today's synchronous lesson. So like in the last 5 minutes or the 5 minutes that we run over time, we're gonna do a workshop photo. So folks on Zoom, we're gonna try to take a Zoom photo of all you all, and then for the folks in person, we'll probably go outside and take a in-person photo, and we'll combine them in post-processing somehow, like we do every year. Okay, so that's right. So don't leave immediately after the end of the workshop, even though I know you all want to. I think that's it. Okay. All right, Sarah, floor is yours.
All right, everybody on Zoom can see my screen? Okay, great. All right, so we're gonna start off the day by talking about Gitflow. The goals of this lesson are that by the end, you're gonna be able to define Gitflow, define the basic Git workflow, create multiple branches within a Git repository, and make a pull request from one branch into another. So before we start, I just want to, there's a lot of vocabulary around Git, and it can be kind of confusing. So I first just want everybody to take a second to try to do this little fun matching game. We're gonna go back to kindergarten and play matching. I'm very excited. So take 2 minutes and just try to match, say A goes to this, and oh my God, I already sorted it. Oh, I'm so sorry.
You were too prepared.
Okay, well, oh, no matching, I'm so sad. Okay, well, you don't get to do it yourself, I did it for you. But let's just briefly remind ourselves what all of these things mean. I was like, why does it start with 5? That's so weird. All right, so Git is a piece of software that defines, reads, and modifies repositories. GitHub is a website that stores repositories. So remember, Git is a thing that does stuff. GitHub is a place for things. Source control is a practice of storing the changes you've made to your code alongside the code itself. People often say source control in the world of software development to mean Git, but that's definitely not the only way you can do it. And even just renaming a file version 1 final is a form of source control. A repository, also known as a repo, is the current version of all code and documentation for a project plus its history. A commit is the smallest unit of a code's history. It's a set of changes. So a fun fact is that at Google, these are actually called CLs, which is short for change lists. I feel like that's actually more intuitive than commit, so thought I'd share that fun fact. A branch is a pointer to a version of the main code that diverges from the main line of development. We're going to talk more about branches in a sec. And to clone is an action to create a copy of the repository that you can edit on your computer. And just to remind you, there's this vocab list here. The vocab list is also in that main list of links, the information about the workshop that you can access on the main page. So why do we need Gitflow? When you're working on big projects, many people are committing code at once. And as we learned yesterday, you can very easily run into merge conflicts. It can get complicated. It can, even if you know how to resolve merge conflicts, it can get really complicated to decide, okay, we want to keep this part of your code and this part of my code, but I edited this and you edited this, what's actually the right thing we want to keep? So Gitflow plus source control allows people to edit the code base at the same time, but maintain their own separate sort of histories of the code. So Gitflow is a way of using Git and GitHub. It's a method. And I'll tell you what it is in a sec, but some advantages of Gitflow is that it allows for this multi-user development and testing. It also protects the main code, so you don't ever push code to the main branch before you know it's working. So that's really nice. You don't ever your users don't all of a sudden have a version of the code that's not working. It also makes it easy to go back to a stable point if something breaks. And it allows this nice feature that work is performed in parallel on one or more feature branches. All right, so let's define how Gitflow actually works. So we start off with the main branch, and then the first thing you do when you create a new repository that follows Gitflow is you create this develop branch. Branches are basically just different like histories. So it's like they diverge from a common point. So back to that common point, they all have the same code. And then you can start editing them independently from there. The next thing you do is create a feature branch. So this is the first thing that will actually like add new stuff to the code. So say I want to like create a plotting functionality, I'll do that on the feature branch. Once the feature branch is done, you merge it into the develop branch using a pull request. And I'll show you a pull request in a sec. And then finally, once develop has had several different changes made and you feel like it's worth making all those changes available to users, you merge the develop branch into the feature branch, into main. Then you keep going from there. You have a new version of develop that maintains the sort of like, develop sort of like collects all of the new features one by one. And this is really nice because you can sort of make sure that all of your new feature branches play nice together on the develop branch. You're not actually doing your testing on the main branch. You're doing everything on develop, making sure that develop works, collecting a bunch of changes, and then once you're happy with that, merging it into the main branch. So just to summarize, Gitflow allows for multi-user development and testing, as you can hopefully now see from this multi-branch setup. It protects the main code by not merging into main any code that you're not sure actually like works well together. And it makes it easy to go back to a stable point. You can always go back to this develop branch if you're not sure if something doesn't work. And then you can also, you don't have to, create only one feature branch. You can have several feature branches. Yep, Maddie. Sorry, can you say that again? Yeah, so the question is, are there any tree visualizations for this? There's a really nice Git VS Code extension. Do you know what it's called?
I forget if it's on by default. It's called Git. I like Git Graph.
Git Graph, yeah. So you can enable it on VS Code, and it'll make one of these nice trees. It sort of turns it vertically rather than horizontally, but you can actually see like the relationships between all of your branches.
Someone remind me. I'll show it when I.
Okay, Jason will show it if someone reminds him. I'll try to remind him too. Great question. All right, so a quick confession before we go on is that I don't actually always follow Gitflow. The reason for this is that we're not industry programmers. The world isn't necessarily going to blow up if somebody gets a version of Orbitize that doesn't completely work. So I tend to sort of turn on and off my usage of Gitflow. I tend not to make a develop branch unless I expect a lot of changes to happen at once. So if I am really worried about lots of changes playing nice together, then I'll make a develop branch, put all that stuff in there, and then merge that into main. Otherwise, if there's just like one change happening at a time, I sort of just merge those into main. So I did use a develop branch when working on this open source code Orbitize that Jason and I developed together before releasing major new versions, and also when working on industry code. It's totally fine for you to figure out what flavor of Gitflow actually works well for you, but it's also worth knowing what the sort of industry standard is, I think. Okay, so now we're gonna do a demo. The main parts of this demo are that I'm gonna show you how to raise an issue in a repository, create and manipulate multiple branches within a Git repo. We're gonna create main, develop, and a feature, how to use these branches, and how to submit a pull request. Okay, so let me pull up my checklist. So we're gonna go to GitHub. The first thing I want to do is create a new repository. We did this yesterday, so you just go to repositories, new. All right, let's use GitHub suggested one, upgraded Octo computing machine. Love that. Okay, I'll make it public, add a README, add a git ignore, and then create the repository. All right, so the first thing we'll do is raise an issue. The issue interface is a really nice way for your users to give you feedback on your code and also for you to sort of keep track of things you need to do. So I will often raise issues in my own repositories as like, this is a thing that I want to remember to do later. It's sort of like a to-do list. But other people can raise issues too. So if there's a bug, it's a really nice way for people to report that to you. So you go up here to this issues and raise a new issue. So let's say we want to add some functionality. Upgraded Octo computing machine is pretty bare at the moment. It doesn't really do anything. So maybe issue 1 can be like print some welcome message, please. Can you all see this, by the way? Is the too small? Okay, make it 1 bigger just for fun. Another couple nice features that are worth pointing out is that you can assign people that have contributed to the repository. So I could assign this to myself. There are also these nice labels, so you can say if it's a bug or an enhancement, etc. We'll say that this is an enhancement since it's new, a new feature that we're requesting. And you can also, there's also this way in GitHub you can keep track of a lot of things that are related with the project, or also set a milestone. All right, so let's create our issue. All right, so the next thing I'm going to do is create a develop branch. So right now you can see this little interface says main, so that means that there's one branch and it's just called main. If we want to create a new branch based off of main, within GitHub, all you just do is type in the new name of the branch here. So see it pops up to create branch develop from main. So from main means that initially develop is just going to be a copy of main. It's going to have all the same code. We'll make changes to it, and then we can merge those changes back into main. All right, so let's create this develop branch. All right. So let's now create a feature branch. So we want to actually add some new stuff to our repository. So we'll do the same process. We're going to say feature 1. And you see here it's creating branch feature 1 from develop. So at this point, feature, develop, and main all have exactly the same code, but they won't shortly. All right. So at this point, we might want to start like doing some development on our own computer and not actually like just rely on the GitHub interface. So I'm going to go through the same process yesterday of cloning the repository. You do this by clicking on the code, clicking on the little clipboard here. I'm not sure if people on Zoom can still see. All right, I'm going to open up VS Code. So if I open a new window, a nice thing about VS Code is that it has, if you open up a new window, it has this automatic like clone repository button. So you can click that. I can either like just type in the repository URL, or I can choose this clone from GitHub and then search for it. So you can see it actually like it finds automatically the first one that the most recent one that I updated. So let's clone it. It's going to ask me where to clone it. I'm going to clone it to where I put all my repositories. And then let's open it. All right, cool. All right, so the branch interface on VS Code lives down here. So you can see right now it says we're on branch main, but if we click on this, you can see that there's 3 different branches that are accessible from the origin. Origin in this case is just the GitHub. So to change to one of these feature branches, on the command line, we would write git checkout. In VS Code, we can just click on it. So let's say we want to go to feature 1. Now you can see down here, we're on the feature 1 branch. Now let's make a change. So our issue was to print a welcome message. So let's maybe make a new file. We can call it welcome, and we'll have something that prints welcome. All right, so now we have made a change. I would like to do the whole process of git adding, git committing this change, pushing it back to the remote, and then merge that code back into main with a pull request. Okay, so let's do that. If we go to the source control tab here, you can see it lists all of the changes. Let me close this so it's a little cleaner. So right now it only says that we have welcome.py. One really nice aspect of this interface that I forgot to show off yesterday is if you click on this from here, oh, I think it only happens if we have changes. Never mind. Maybe I'll show it to you in a sec. But because we've created a file, it doesn't show us anything. But if you've changed a file and you click on it from this source control tab in VS Code, it'll show you side to side, like the old version and the new version, so you can easily compare. So that's why I struggled with git diff yesterday, because I never actually use git diff. I always just use this VS Code version of this. All right, so we've made our change. We want to git add it, which is the same thing as just clicking this little plus button in VS Code. And then we'll commit it. We'll type in a message. Let's say added welcome statement. We'll commit. Oh, I spelled statement wrong. That's fine. Made the change. We're then going to sync these changes to GitHub. So you can now see if we go back to GitHub, it has this nice little thing that pops up that says, oh, just so you know, feature 1 had some changes. It's encouraging us here to make a pull request. It's saying, well, you just pushed some changes to GitHub. You might be interested in pulling those changes back into another branch. I also just want to show you what the repository actually looks like right now. So first, we're on feature 1 branch here. If we refresh the page, you can see welcome.py is there. So the changes have been synced to GitHub at this point. If we go back to the other branches, though, welcome.py is not there. So welcome.py only exists on this other branch. All right, so now we're going to create a pull request. So in Gitflow, the first step is to make a pull request from our feature branch to the develop branch. And then once we have several things that we're happy with in develop, we'll merge that directly into main. So let's create a pull request. You can click this button, or you can just go to this pull request tab. I'll show you just from here. So I'll create a new pull request. This little interface shows you what you are pushing into what you are merging into what. So we're going to take the changes from feature 1 and merge them into develop. And then it's showing us this nice interface that gives a summary of all the changes that have been made. So you can see it's saying, okay, you've got one change, one addition of one line of code. It'll show things as green or red, depending on whether you added or deleted code. We can then create this pull request. It's generally good practice to give a little description of what actually changed in your pull request. I'm really notoriously bad at this. Jason's always asking me for more information about my pull requests. But yeah, generally like a couple of like bullet points about like, here's what I actually changed. Another thing that's really good to do is to tag particular issues that you addressed in this pull request, so that you can have sort of this internal record in your repository of this pull request was to address this issue was opened because of this, blah, blah, blah. So let's say addresses number 1. So this tags this issue. We'll then create this pull request. All right, GitHub is going to do some internal checks. Later in the week, we're going to talk about testing and a practice called continuous integration, which is this idea that a suite of tests is run every time you make changes to your code or every time you open a new pull request. So this is the point at which these tests would start running automatically. But then, yeah, that's pretty much it. The final thing to do is to merge this pull request. So let's do that here. It's going to ask us for a commit message. And then we can confirm the merge. All right, so now everything's been merged together. Best practice is to actually delete your feature branch once everything's been merged in. In Git, nothing is ever like really deleted. Like you can always go back in the history and find it. But this sort of keeps you a little bit more organized. You don't have feature branches that correspond to changes that have already been made. So we'll delete the branch. And then if we go back to our code, you can see now we only have 2 branches, and then develop now has this welcome.py change that's been made in it. Another thing I'll generally do at this point is close the issue if it's been addressed. So I have like these sort of the pull request referencing the issue and the issue referencing the pull request. So if you ever pull up an issue or an old pull request, you have this record of what it was for. So let's say addressed in, and then I'll tag the pull request, and then I can close it. Yeah, so that's pretty much the whole process of Gitflow. I think we've got 10-ish minutes. So the next thing that I want to do is just give you a little bit of time to actually practice doing this with your project groups. Yep, question?
What happens on VS Code, and how do you make sure that your VS Code is now updated with the deleted branch?
Yeah, great question. So first, we can, one thing I forgot to say yesterday is that this little thing here will run a git fetch, which like makes your local code aware of changes that have happened on the GitHub. One other thing to note is that you can have different branches on your local copy and in GitHub. So it's you have to like do some things to like you have to be a little bit careful. You can track local branches to push to remote branches though. So let's see what this actually looks like in practice. So if we synchronize it, it's saying, oh, I can't find this remote, so I can't actually pull these changes down. So what we might do here now is to change back to develop, and then we can, well, let me show you what develop looks like right now. Oh, it already synced it, just kidding. So it already pulled it down. Yeah. Mm-hmm.
Question, so when you merge the pull request, is there a way for GitHub to automatically delete the branch when you merge it, or do you have to do that manually?
Yeah, the question is there a way for GitHub to automatically delete the branch once you merge it? I don't know. I always have done it automatically. There must be some, there's this whole framework that we'll learn about later in the week called GitHub Actions, which is basically like do things automatically when stuff happens on GitHub. So I'm sure there's a GitHub action to automatically delete the branch. Yeah, I don't know. Do you have any thoughts about that?
Never
Yeah.
bothered me.
Yeah, I always do it automatically or manually. Any other questions? All right, awesome. Thanks, guys. Okay, so, so the summary of the process to add a feature, you pull the latest code from the developer main branch to make sure that you are actually starting from a version of the code that's current. You then create a feature branch, make your changes, stage, which is git add, commit, and then push to feature branch. Submit your pull request on GitHub and then merge that feature into develop, or if you're not using develop, just into main. And then if you are using develop, repeat until enough features have been merged, then make a pull request from develop into main. All right. Okay, so we'll just spend 10 minutes doing this, and then you can continue doing this with your project groups this afternoon. So we encourage you to create a repository, either a dummy repository, like one just like what I did with the Octo, whatever, or using the repository for your project. Then we encourage you to create a main, develop, and at least 2 feature branches, so 1 for each person at this point. Also practice raising an issue, clone the repository to your machine, make the changes on each of these branches, and then open pull requests, and then perform the merges. One note is that in order for people to push to the same repository, the repository creator is going to need to add everybody as collaborators. So you do this on GitHub by going to settings, collaborators, and then add people, and then your permission should be okay. All right, so let's spend 10 minutes doing this, and then we'll move on. So we'll come back at 40 after. All right, everybody, let's get back started. Okay, let's take a 10-minute break, and then we're gonna go on to the next lessons. One thing I forgot to mention is that these slides are these are available in the day 1 directory, because we originally were planning to do it on day 1, so that was a little confusing. Okay, yeah. So we'll come back together at 52 after the hour. Okay.
let's get back started. We've now talked quite a bit about Git. You've used it from the command line, you used it from VS Code, you use Gitflow, and you're just like, here are some commands I type and magic happens in the back, and some things eventually, if I type the series of commands that someone on the internet or has told me to type, hopefully things are in the right space, right? And you're just you basically are kind of like hoping that what you hit did the thing you wanted to hit. So for purpose of this next hour, we're going to try to develop a mental model of Git so that we can kind of reason through what we should be doing. Like, what is our current Git source tree looking like? And what command do I want to type in order to do something to my Git source tree to make it something else? So we're going to go through this new model, this kind of mental model of Git. It is not actually exactly what happens under the hood of Git. What happens under the hood of Git is it's just kind of like another level of abstraction below it. There's like an actual real implementation of Git below that is just way too complicated, that doesn't actually help you at all in terms of reasoning through it. So this isn't exactly what happens under the hood, but it's a useful abstraction for what's happening under the hood. Okay. So we talked about this thing called git commit. So so next hour we're actually not gonna do anything on your computers. This is gonna be like we're gonna do pen and paper Git basically, from your physics training. Instead of doing things on computers, we're gonna solve it by hand. We're gonna solve Git by hand. So think of a git commit as an object. So we talked about objects yesterday. Objects are a useful thing to kind of track the state of things. Our git commit is itself, think of it as an object. The git commit has a bunch of things. So this circle we have here represents the git commit. We have, one second. This circle here represents the git commit. The git commit has a lot. It has a lot of stuff. It has an ID. An ID is a series of letters and numbers, as you are now probably acquainted with. It could also have a parent ID. What is the commit that this commit spawned from? And that parent ID also is a series of numbers and letters. This git commit has a list of changes. Maybe we created a new file input.py and we added text starting at line 0. Maybe we modified another file called plot.py. We added text at line 12 and deleted text at line 36. It's a series. These are all like the various things that you get added to your commit. Like I get added input.py, get added plot.py. You added all those changes to your commit. And then it also has some message. This is your -m. When you do git commit -m and you type in a message, that message is stored in that git commit. Also, it has things like your author, your email, and the time that the commit was made. Those are like metadata that as part of the commit. So this is all like things that is encapsulated in a single git commit. It has some identification. It knows what its parent git commit is. It knows the list of changes that were made in that commit. And it knows who made that commit. So this is our git object. So this object has a bunch of different attributes that were populated. This is kind of the atomic unit for a model. We're not subdividing anything beyond a git commit. So that's why when people asked yesterday, what is a commit? Like, how often should we make commits? You want to make a commit that's sufficiently small enough. You never want to subdivide it. You don't ever want to split up half the changes from the commit and keep the other half. You want to everything in a change. All the changes in the commit kind of all are together and not divisible, basically. And a git repo will consist of a chain of git commits. You can imagine a single git commit has a parent commit, and that parent commit has its parent and its parent and its parent and its parent, so on. You can make a chain of git commits. So we're gonna do this. We're really doing git by hand. We're gonna see what happens to the git commit tree as we type git commands. So we're gonna pretend we're gonna make a package that makes color images and plots them. So this is like our colored astronomical, like false color image plotting package. So we first type git init, and that initializes the folders. It makes it be like we have a folder that is tracked by Git. Then we actually do some code. So we go type, and we maybe add code to this file called color.py to generate color images. That's the actual programming that gets done. So after we do that, we type git add color.py, git commit -m initial commit. And you'll see from your terminal, you've experienced this now, you'll get like something like main 309f initial commit, one file's changed, create color.py. And that's what your terminal outputs when you run that command. Now we're not pushing anything to GitHub, we're just doing this all locally. So when you do that, our git commit tree now looks like this. We have a single commit 309f. Its ID is 309f. Its parent ID is none because this is the initial commit. It's the first commit in our git commit tree. The changes is that we've created this file color.py and we've added text on line 0, and the message is initial commit. So this is our first commit in the git commit tree. This is what happened behind the scenes when you typed these series of commands. All right, so we'll keep programming. So we'll keep going type, and make some changes to color.py. In this case, we fixed the bug where our red colors weren't displaying in our plots. So to add these changes to our git commit history, we do git add color.py again, git commit -m, fix red color bug, and then our terminal would output main 8a6c fix red color bug, one file's changed. And what has happened now is that our git commit tree looks like two commits. We have 309f and 8a6c. 8a6c, its attributes look like this. Its ID is 8a6c. Its parent ID is 309f, so it knows where its parent is. And the changes are we modified color.py, we've added text on line 12 and deleted text on line 36, and we have our message. One thing to note is that I drew this arrow in a very particular way. This arrow from 8a6c points to 309f. Now recall, 8a6c knows that its parent is 309f, but its parent 309f, if you remember its attributes, there's no attributes of child, right? We don't know. 309f does not know about 8a6c. It only knows about what happens before it. So any commit doesn't know about what happens after it. It only knows about things that happened before it. That's something important to remember. We're going to drop the arrow moving forwards because it was really hard to keep the arrows there in PowerPoint and make everything else, and it was just too busy. So we're dropping the arrow in the future, but just remember that every git commit only knows about its parent. The parent doesn't know about what happens after it. So we can keep going. We wrote a plotting module that basically displays our color images. So maybe we want to add that plotting module to our git commit tree. Go type, and then we do git add plot.py, git commit -m added plotting, and then our terminal will output main 91e1 added plotting, one file's changed, created plot.py. And what has happened now, just like before, we have a new commit 91e1. 91e1's parent ID is 8a6c. As changes are create plot.py, add text on line 0, and it has a message. And again, 91e1 knows about 8a6c, which knows about 309f, and that's how we reconstruct our git commit tree. But if we start in 309f, it knows nothing about 8a6c, and it knows nothing about 91e1. So to reconstruct the git commit tree, we have to know about the latest commit in our git timeline to be able to go back and reconstruct the full git commit history. Okay, so here we're going to introduce about what are git branches. Branches, as we've shown, are ways to basically work on separate features in parallel. We've seen this in the Gitflow. So what are actually branches? Branches aren't commits. Branches in this model, and really what's happening under the hood in Git, is that branches are just essentially pointers to the most recent commit. A pointer is something in programming that doesn't in itself hold any information. It just points you to where the information is held. So in this case, we start off on the main branch. The main branch is just a pointer to the latest commit on the main branch. So the main branch literally what happens inside of Git and also in our model is that the main branch is literally this main 91e1. That's all it is. So then to figure out what is your main branch, You go main 91E1, 91E1 is here, its parent is 8A6C, its parent is 309F, and that's the end. So now from that, we've reconstructed the main branch. So that's all a branch is. A branch is just the pointer to the latest commit in that Git timeline. So this is why branches are, this is why in Gitflow, we make lots of branches. Branches are free, basically. They're just pointers to commits. Commits have a lot more stuff encapsulated in them. Branches are just pointers. So we can make as many pointers as you want. The head, there's another special pointer called the head pointer. The head pointer is where you're currently, what branch you are what state are you currently at in your Git repository. So right now we are at the 91E1 commit. So our head pointer is telling us that we are at 91E1. Well, the head pointer is telling us we are on the main branch, which is at 91E1. So we're on the main branch right now and is at 91E1. So the head pointer and main are all pointed at 91E1. So just to keep these things separate, branches point to where information is, but doesn't contain data. Commits don't think about which branch they are a part of. They just contain changes. Good. Okay, we covered everything. So let's say we want to make a new branch. We're gonna I want to make my plotting interactive so that we can just adjust the coloring by eye. But we have all our code working right now. We don't want to break the current code. So we're gonna make a new branch to work on this new feature without breaking the main code. So we're gonna make a new branch. So we're gonna do git branch plot upgrade. So that creates this new branch called plot upgrade. We do a git status. We're still on the main branch. We've made this branch, but we haven't switched to it. So the only thing that's changed between the previous slide and this slide is that in our list of branches, we have a new branch called plot upgrade, which also points at 91E1. So here, our git commit tree looks the same. Our head pointer is still pointed at the main branch, which is pointed at 91E1. So both the main branch and plot upgrade point at 91E1. So both branches look exactly the same. If you ask what the plot upgrade branch looks like, it looks like this. If you ask what the main branch looks like, it also looks like this. So then we can switch to that new branch, git checkout plot upgrade, and then we do a git status. We've now changed to the plot upgrade branch. What has happened is that nothing in the commits have changed. We have not changed any commits. All we've done is, and we haven't even changed the branches either. All we've done is change the head pointer. The head pointer is telling you where are we currently located in the git commit tree, and the head pointer we've now switched to, we're now located on the plot upgrade branch, which is at 91E1. So now we'll make some edits to our interactive plotting code. We go type, and we do git add color.py, git add plot.py, git commit -m interactive. And now we've made a new commit in plot, and our terminal will return plot upgrade 353b interactive. Two files have changed. So what has happened now in our git commit tree, and I purposely kind of moved this to the side, is that we have a new commit 353b. Its parent is 91E1. And notice that how the main branch has stayed the same. The main branch is still pointing at 91E1. So if you go to the main branch still looks like 91E1, 8A63, 309F. Whereas the plot upgrade branch now looks like its most recent commit is 353B, and our head pointer is still pointed at the plot upgrade branch. So our current branch and the plot upgrade branch is 353B, 91E1, 8A63, 309F. So we've reconstructed our git commit history for this new branch plot upgrade now, which is now one commit ahead of the previous branch. Let's say, while we were doing all of that, we found a bug in our main branch code, our regular plotting code, and we wanted to fix it. What we can do is we do a git checkout main and git status. And what will happen is that we've now switched to the main branch. We will make edits to some file, say colors.py, and then we make a new commit, git add color.py, git commit -m, fix nans. And then this will output a new message, main A329 fix nans, one file changed. And you'll see that we now have a new commit A329, and our main branch is now pointed at A329, and our head pointer is also pointed at the main branch at A329. A329, our main branch now has 4 commits that go like this, and our plot upgrade branch still has those 4 commits that go like this. So we've now shown like what happens with switching branches. Switching branches is basically just switching pointers, and switching pointers and branches just pointers, and switching branches switches to what pointer should we point to, and from that we can reconstruct the whole commit history and thus reconstruct what our code should look like on any branch.
Excuse me,
Yes,
to the previous slide,
yes.
so it says that 2 files have changed. So why 2 files?
Here we've added we've done a git add color.py and a git add plot.py. So both of those files are in the changes of the 353b git commit. So that's why it says 2 files have changed. Yeah. Yeah. So you don't like a commit doesn't necessarily only change 1 file. Yeah. Yes.
So if you find a bug in your main branch while you're working on a new feature, the best practice is just to fix it on the main branch or the root branch, the full stack part that has the bug, and then later merge in your development branch, or would you fix it both?
I think it depends. I think it depends if that bug that you found affects your new development branch or if it doesn't affect your new development branch. If it affects your new development branch, you want to fix it in both. If it doesn't, you can fix it in one. Yeah. Okay, so we've now talked about git branches, git checkouts, and we've talked about diverging branches. Now, what happens when we do a git merge? Git merge is the most magical one. So let's say we've tested our code in the plot upgrade branch. We think it works. So let's merge these changes back into main. This could be done through a pull request. This could be done with just literally running git merge from the command line. But either way, this is what happens. So let's first, if we go git checkout main, git status will be on the main branch. We'll be on the main branch just like before. We're right here. And then if we do a git merge plot upgrade, and this is what a pull request also does. If you pull request from plot upgrade to main, it does the same thing. It creates a merge commit. If there are no conflicts, Git will automatically make this merge commit. This merge commit 8443. It has an ID 8443, and it's special because instead of having 1 parent ID, it has 2 parent IDs. It has we're merging from 353b into A329. So it's a merge commit that merges 2 branches, and because of that, there's kind of like 2 parents that come together that create this to create this merge. And it also has changes. You know, we modified color.py, and we probably modify some other files, and it has automatic message merge branch plot upgrade. Yes.
So you're saying this is the same thing as a pull request, or this is different?
This is the same thing as a pull request. Under the hood, this is the same thing as the pull request. Running your command git merge plot upgrade from a command line is the same thing as doing the pull request. So yeah, if there are no conflicts, it automatically makes this commit, and that's all you have. You have this new your main branch is now at 8443, and to reconstruct the main branch is 8443, A329, 91E1, etc. And our plot upgrade branch, nothing has happened to it, right? No one has touched anything to it. We merged changes from it, but the branch itself remains the same. It's still 353b, 91E1, etc. So the plot upgrade branch hasn't been destroyed, hasn't been changed. We haven't deleted it or anything. And deleting the branch from a pull request, as we talked about before, is literally just striking out this thing. Nothing has happened. This is what Sarah means by nothing has happened to your commit history. Like all the commits still are there. Just deleting a branch removes this line from the Git repository. So it just removes that pointer. That pointer no longer exists. It's very easy to add and delete branches. Okay, questions?
I think I get a little lost. This might be a silly question. If you make a change on the main branch, let's say you like caught a bug, debugged it, put it as the main, and then you have this feature branch like plot upgrade.
Yeah.
And it's the same as main, other than I don't know, you change the different file.
Yeah.
Debug something else.
Yeah.
You can merge.
Yeah.
What like do they now become the exact same thing, or does the main debug that stays there, and then like it now also takes this other thing to change.
Yeah, it's a good question. So here, we have changes in A329 and we have changes in 353B. If those changes don't conflict, we can just take the union of the changes. So accept all the changes from A329 and all the changes from 353B. And that's in, so basically 8443, basically, we already have the changes from A329 in main. So what we've done is added in all the changes from 353B and put it into the main branch by adding them into 8443.
Yeah.
What you can think of it is all the changes from this branch. If there are multiple commits, all the changes from all the commits from that branch are in this commit, basically.
It's
That's the next slide. Any questions? Okay, what if they do conflict? We run the exact same commands, and instead of it auto merging, we get conflict, merge conflict in color.py. So our edits in color.py conflict. So what we have to do, it's the same as before. We have to manually change, we have to manually fix the commits ourselves, right? We have, let's say, in this case, maybe we added this keyword mask nans, and then equals to false in the main branch, and in the plot upgrade branch, we added this keyword interactive equals to false. So they both modified the same line of code. Git obviously doesn't know how to program, so it's like, what do you want me to do with this? So we need so what it does is basically if you now experience it tells you that the head, our current main branch, looks like this. The incoming branch looks like this. What do you want me to do? Right. So VS Code has some cool syntax hiding codes for Git conflicts, but this is something where you have to manually fix it yourself. We've decided through manual code editing, we just want to keep both keywords, so let's keep both of them there. And what we can do is add these new, we made changes, right? These are just changes, and these are changes like any other Git changes. We can add these changes into our merge commit. So our merge commit 8443 now not only contains all the changes from the 353B feature branch, it also contains the changes that we manually made to fix the conflicts. So from this kind of high level, this is our toy model of the Git commit history. A merge commit with conflicts looks the same as any other merge commit. It's just that the conflicts are part of the changes in this. The fixing of the conflicts is part of the changes in this Git commit. That's the only difference. Yes.
Does it matter which branch we're on when we make those changes? So
What?
if you're editing that one line on the file, should you edit it on the branch or the main before you do that?
So anytime you're merging, you are merging changes from a branch to a branch. So the branch that you're merging to is the branch that you're editing. We're not touching the commit that we're merging. You can see here, the plot upgrade branch has not changed at all. The plot upgrade branch stays at 353B. The main branch has advanced from A329 to 8443. So again, this commit itself doesn't care about anything, right? It doesn't care about branches. It only cares about changes. But for the branches, only the main branch follows this merge commit. The branch that you merged the changes from does not follow this merge commit. It doesn't. The branch that you merge the changes from does not advance its branch pointer. It's only the branch that you merge the changes into advances its pointer to this new commit. Does that make sense? So all the changes you made go into this commit, which itself doesn't care about anything, but practically for Git, it only moves the branch that you're merging into. It only moves the pointer of the branch that you're merging into to that new merge commit. Okay. So yeah, so this from our tree looks the same, but we all know that we went through a bunch of hard work to actually fix those manual conflicts. But for the purposes of Git, it basically just thinks of those manual changes as other changes that went into the changes attribute of this commit. Okay, so that's kind of a short lesson into kind of a mental model of Git. I think the best way to kind of practice this is to do a couple of activities. So we have two activities for you. Try to at least get through the first one, and then you can try to do the second one as well if you have time. The first activity is, let's say that this is the current state of the branch on our computer. We have 309F, 886C, 91E1. And we've now, since now, only talked about the Git commit history on our local machines. We haven't talked about pushing and pulling from GitHub yet. So I want you to think about, how does this mental model work if we start pulling and pushing from GitHub? So we're going to run git pull to pull updates from remote, such as GitHub. So draw out what happens to our git commit tree in each of the following scenarios. The remote tree is ahead by an extra commit 832E. The remote branch also has 3 commits, but the third commit, instead of being but the third commit is A32E instead of 91E1. So the remote branch looks like 309F, 886C, 832E instead of 91E1. In both of those cases, try to guess what this thing will look like. If you're confused, make a test repo, just like we've been doing for the last 2 activities, and just try it out. See what happens. See what Git actually does, and try to update your mental model to try to match that. The second activity is something that you probably will run into. Oops, I've committed something. I've accidentally committed something and it's totally wrong. I want to get rid of the changes I made in 91E1. Maybe this is something that you'll run into. Here are 2 ways that the internet tells us of how to revert those commits. These are 2 ways. They're not exhaustive, but they're 2 ways. The first way is git revert 91E1, and the second way is git reset -- hard 886C. You can learn about what these commands do online, or make a fake GitHub repository and try them out, and draw what happens to the git commit tree in these 2 cases. So the goal of these exercises is kind of build up this mental model of how Git works in your inside of your head, and try to guess your way through what you should be doing in each of these scenarios, basically. So we'll have, let's say, 25 minutes. So we'll try to end at 55 minutes after the hour. So for folks right, and we'll have a Piazza post for you to post your responses to the 2 answers in. So you can do this on pen and paper to take a photo of it. For people on Zoom, in your breakout rooms, you can share screen, use like the whiteboard app, or use a PowerPoint to draw these out with your group members. But try to reason them through together, and figure it out. And this PowerPoint should be on the day 2 GitHub, the day 2 folder in the code Astro in the README. So if you need to find these diagrams and things like that, you can find them there. Okay. So let's come back at 55 minutes after the hour. Okay. Okay. Let's wrap up. So let's take a look at what you guys said for activity 1. So this was syncing with GitHub and thinking about what happens to a git commit tree when we sync with GitHub. So in the first case, the remote GitHub is ahead by an extra commit, A32E. And in the second case, the remote branch also has 3 commits, but the third commit is A32E instead of 91E1. So let's take a look. So here, this looks like the first scenario where GitHub is ahead by an extra commit, A32E. So when you run git pull, our local branch also, our local branch was this, and it recognized that GitHub had an extra commit in the timeline. So it just pulled that extra change in, and it looks just like this. So we've just basically synced between the 2 branches. In the second case, in the second case, our branch looked like this, and then GitHub looked like this. So those are 2 diverging timelines on the same branch. And what happens when we have a diverging timeline? We have to merge them. So yes, so we have to make an extra merge commit that merges these 2. So if you run a git pull and there are no conflicts, then you will get this merge commit that merges the changes from the 2 branches together. Good. Yeah, so sometimes running git pull will actually give you extra commits, because if you are divergent with merge, with main, you will have to make a merge commit as part of git pull to get that extra, to get those changes in. Very good. Look at activity 2. This looks like from the first one. Okay, this is scenario 2. All right, let's remind ourselves what the scenarios are because I already forgotten to. Okay, in this one, we did something wrong in 91E1 and we want to get rid of those changes. So I have two options: get revert 91E1 and get reset dash dash hard 8A6C. So this is a merge of two, which is not quite yet. Here, I'll show you what's in the answer key. This one is a little bit trickier. So a get revert of 91E1 looks like this, and a get reset hard of 8A6C looks like this. So what I've done in a get revert 91E1 is I've made a new commit that's like the antimatter to the matter of 91E1. I've basically made changes, the exact opposite changes in 91E1 to these two commits cancel each other out and basically restore us back to the 8A6C. But we have not removed 91E1 from the timeline. 91E1 still remains in this timeline. We're just made a new commit along that basically cancels out those changes, but still recording those changes that did exist in 91E1. Here, a get reset dash dash hard 8A6C, what we've literally done is move the head pointer. We moved the main branch to point at 8A6C. And remember, 8A6C has no knowledge of its children. So the main branch now just looks like 8A6C 309F, and 91E1 has been erased from history forever. You can see that maybe you don't want to do this very often. I only do this in cases where I've maybe accidentally uploaded a 2 gigabyte files in 91E1. I do not want that in my Git repository forever. You can imagine in this case that 2 gigabyte file remains because it's always in your timeline. Here, by forcibly removing it from the timeline, that commit disappears. So it's an option when you've accidentally committed something to GitHub that you absolutely do not, you want to erase permanently forever, but use this very sparingly. Question?
Seconds, as vacancy and uploaded like a key that lets them access something private or something you really don't want on the internet. Does this, how rid of things does this?
So the question was if someone uploaded a password to your Git repo and you want to do this, how rid of everything does it get? The best security practices is always at that point you assume that password has been leaked and you should reset that password. This does delete it from the repo. Deleting things from the cloud is not something you have control over, and depends on how GitHub decides when to actually really delete things and when it will, because it will probably keep it for a while because it costs money to delete things immediately when you want to delete things. And rather, it's a lot more efficient to delete things later on when they do a batch delete of a bunch of stuff. So you should always assume if you accidentally pushed your password to GitHub, which you should never do. But if you do, you should assume you should need to change it because that's usually the best practices. Any other questions on this activity? Yes.
So would we, the possible like name it something like set instead of just, or are the IDs right then, or how would you access?
Oh, so the question is, how do I access these IDs, right? Because we have to be able to identify these Git commits. All right, yeah, so you kind of have to figure out what the IDs are. So maybe this is a time to actually pull out VS Code because I said I was probably going to show you the Git graph. This is what if you install the Git graph module extension in the source control panel. In addition to the regular source control part, I also have this graph, and this basically like shows you what all the commits are. And if you hover over a commit that you don't like, the ID is right there, and you can copy it. From the command line, you can use things like git log. Okay, we've gone too big. I can't even see what I'm typing. I still can't hide meeting controls. Okay, you can type something like git log, and it'll, for each commit, it'll give you the full ID. Sometimes this is very long. If you just copy the first 6 characters, usually it's enough to know. But you can you can go through and look at the whole Git commit history from here as well. Although I generally prefer to look at it through something like this. It makes it a little bit easier. But you can grab this, and they even have a nice little feature where you can just copy this to the clipboard, so you don't have to remember it. But yes, you do have to specify these very obscure hexadecimal characters. Any other questions? Yeah.
The second scenario in the previous slide, the slide number 2. If there is any kind of conflict between 832E and 91E1,
this is when it will pull and give you conflicts, and you will have to manually fix the conflicts. And just like every other merge commit, those conflicts are buried in that merge commit as part of its changes. Yes. This is like you'll sometimes have this will happen. You do a git pull and it'll say there's conflicts, and then it'll create a commit for you that's like partially made, and it makes you finish the rest of the commit before you can add that commit. Okay, let's stop here. Let's take a 10-minute break. Let's take a 10-minute break. We'll resume at 5 minutes after the hour. Let's get back started, everyone. All right. So we're gonna now, for the last hour today, talk about debugging, everyone's favorite activity. So yes, we love to hear the excitement. Let's take a second to appreciate the meme, our vintage memes of Code Astro. All right. Yes. So, how do we make debugging less painful? I'm sure everyone here has, have some debugging tools. No, whatever, of different ranges. Today, we're going to show you particularly how to debug within VS Code try to use as many features of the IDE to help you to debug. It's a little bit of a learning curve, and at first you'll be like, this is taking me way more time to debug things than my normal strategy, which could be true, but we feel like if you take some time and invest in it, it will help you in the long run, which is why we want to get you started on this. So we're going to start off with a little debug demo. This is some code that lives inside of the day 2 folder. There's going to be something called debug_matrix.py. I had to write this code to be purposely broken. It's very hard to write code with bugs in it and make the bugs any bit useful. So bear with me. The main point of this exercise is to show you the debugging tools of VS Code, not to be like, this is how we solve impossibly difficult bugs, because the bugs themselves are probably not that complicated. It's just we're using the tools of VS Code to show you, what kind of capabilities you have for debugging. So we have this file called debug_matrix.py, and let's just try to run it and see what happens. So if I run, I really do have to hide reading controls. Okay, hide from controls. Press escape. Okay. So if I try to run this code, it's gonna crash, I think. It shouldn't also take this long for Python to load. Okay. There we go. It crashed. Great. That's exactly what I wanted. It's a code crash. You're like, we have to debug it. There's something happening somewhere, and we need to debug it. Okay, so that's maybe your normal flow. What we're going to show you is the debug console in VS Code. So we can also run this code in debug mode. The debug console of VS Code uses something called PDB. PDB stands for the Python debugger. This is a Python library that comes with Python for debugging. It comes only with command line by default, and it's very clunky to use, but VS Code kind of wraps, and all other IDEs like PyCharm wrap PDB in a way that has a lot more, that looks a lot nicer, and you'll see that in a second. So to enter debug mode, we have to go to the left-hand side here and click on this little bug button, run and debug. I already have a debug environment enabled, but let's pretend that I don't have this. So I'm just going to delete this entirety and save it. Okay, so if you come here from scratch, if you open this, you'll see this instead. It'll say you'll need to open a file to be ran and debugged. So let's open debug matrix, and then it's gonna say you need you should probably create a custom run and debug configuration file. So resist the temptation to hit this big blue button. It works, but this is better. Let's just set up a configuration environment first. So let's say we'll create a launch.json file. So this will create a Python debugger, and I want to debug the current active file in Python. So that's all I'm going to click. Click the first one, and it creates a debug configuration for you. And then if I hit save, now I have a single debug option, which is Python debugger debug current file here. Before I run it, just one helpful pro tip is we're going to add in an extra setting. And that extra setting is available that we have a demo launch.json file. It's the same thing as this, but it's a demo version. And the demo version has an extra line called CWD file dir name. And this doesn't affect this current demo, but in general, I like adding this extra line in because this sets your current working directory to the directory that the file exists in. And that usually just makes it easier because sometimes you open it up and you don't know which directory you're running from in debug mode. This forces it so that we're always running in debug mode in the directory that your file lives in. And this, especially if you're playing with file paths and trying to figure out paths to various files, this makes it a lot more clear where you're debugging from. So that's an extra thing that doesn't come from by default, but I like to add that in, and it's available in the day 2 folder. We have a demo configuration file that you can copy that from. Okay, so now I've saved it. We should be okay. I have to go reopen debug matrix. Okay, so here we're gonna now debug this code. We already know it crashes. But we want to run it and see where it crashes. So I'm just gonna hit run, and this is just gonna run the code in debug mode, and it's gonna run until we crash or until it ends. Here so this is loading it up. I'm gonna make this smaller. Let's see this right now. And it's gonna run. Normally it doesn't. Oh, there we go. It crashed right here. There you go. You got your exception value. Exception has occurred a value error setting an array element with a sequence. So when you're here, basically Python stops the code right when your code crashes. So you can actually inspect the entire state of your code at the time it crashed. So I can hover over a new image, and you'll see that this is an array. It has a bunch of zeros in it. It has a shape of 105 by 35. This is a NumPy array. I can hover over J is 0. I can hover over I is 0. I can hover over pixel RGB. This is some tuple of things, 0, 0, 0.4325, blah, 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 blah. So you can basically inspect everything and try to understand if this is what you expect. Wait a second, I have to open up my script because I know how to fix everything. I have to pretend I don't. Okay. One other nice aspect of the debug console, one other nice aspect of this debug mode is we've crashed here. We have the state of the program when it crashed. In VS Code, we can also go to on the bottom. Normally, you've always been in terminal. You can move over here to debug console. Debug console is a place where you can type arbitrary Python commands wherever your debugger has stopped. I can type 1 + 1. Don't tell me it's 2. You know, I can run anything I want. I can be like, does this work? Set that equal to 1, and be like, that does work. And now I can print it out, and it is indeed 1. Set equal to 2. You know, this is like just running commands line iteratively, basically. It kind of lets you. It's a playground where you can test why things don't work. You'd be like, oh, this does work here, but if I copy this line of code and try to run it, that doesn't work. Okay, so there's something wrong with setting that. And it's probably because this thing is not a single element. We're setting it into a tuple, and that doesn't work. So that's a nice way to kind of this is called post-mortem debugging, and basically you're debugging when your code crashes. Let's say, okay, I want to understand why pixel RGB is a tuple. I see in this line of code, pixel RGB right above it comes from this function called generate RGB pixel. Let's see what happens, see what goes on inside that function. I want to stop the code before it crashes to see what goes on inside that function. You could write a bunch of print statements, or we can use what's called a breakpoint. So if you hover over your line numbers, you'll see that this little red dot starts appearing. This red dot is what's called a breakpoint. And if I click it, I will set a breakpoint at a particular line. So if I can use, I can basically restart the debugger, or I can just basically start over and rerun this from scratch. Now my code will run until I hit a breakpoint. So my code will run until I either crash or hit a breakpoint. And you can see that I've set my breakpoint so that it will hit the breakpoint first before my code crashes. So my code has now stopped here. Just like when our code crashes, we can do whatever we want here. We can inspect variables. We can we can open the debug console and type of whatever we want in here. But the other thing we can do is that we've hovered over this line of code. It's just saying that this is the next line of code that Python will execute. What do you want me to do now that I've stopped here? So we haven't executed this line of code yet. This pixel RGB has not been set. It has not been defined yet. Here, if you notice at the very top, there's actually this control bar up here. This lets you control the execution of your Python script line by line. There are things like step over, step into, step out of, restart, stop. Like restart and stop make a lot of sense. These three maybe don't make a lot of intuitive sense. Like what is a step into, a step out of, a step over? A step into is basically I want to step into this function that's being called. There's a function being called here, and I want to step into that function. So if I click step into, it's going to go into this function, and now the next line to execute is the first line of that function. So we've stepped into this function that was the next line to be called. So instead of executing that function automatically on one line, we're going to execute that function line by line as that function is defined. Step over is basically execute this next line that's highlighted. So step over will execute the highlighted yellow line. So this will step over, we'll run that line. We've now set red equal to 0. Now green is still undefined, but we step over again. Green has been executed. So step into allows us to execute every line by line. Here we're like, oh, okay, we understand this function. This function just has some algorithm to create red, blue, and green, and then returns that as a tuple. That's why our pixel RGB is set as a tuple, because it's red, green, and blue. All right, so we're done with this function. Maybe this function is actually 100 lines long, and we don't want to click step over 100 times to finish this function. Step out of will execute the remaining lines of that function and return to your previous function that you called from. You can figure out with the previous function that you called from here. This is called the call stack. The call stack is basically how deep are you within your function. The module is your Python script. If you call a function within your module, you've now gone one level in. You have one function on the stack. If that function calls another function, then you've gone 2 levels in, 2 functions on the stack, and so on. And then stepping out of will step you out of one level of that stack. Here, we've only stepped into one level of the stack. The only function we've called from our Python script is generate pixel RGB. So step out of will take us out of that function. So it will execute the remaining lines of the code. There's only 2 more lines of code to execute here. The highlighted line and the return line is going to do that all automatically. And step out of will basically have executed this line of function, this function. And now if we click step over, we'll have executed that whole line. Now pixel RGB gets set. And now we understand, we're able to dive into that piece of code and basically understand that code line by line. And you can do that recursively, function within a function within a function if you need to. This is particularly useful when you're going into functions that maybe you didn't write yourself, or there's like functions spread over many files. You don't want to try to figure out which file to open at which line number to find each of those functions. It will automatically get you to those. Okay. So here we've kind of identified that pixel RGB outputs a 3-element tuple. Pixel RGB is 3 numbers, and we're trying to set that to something, and new image j, I is 1 number. So that's not going to work. So let's see how slow do we go to here? I think we've okay. The solution to this is basically we know that we're creating. I just need to do this. I'm pretty sure. Let's see. Oh, okay. Yeah. The debug console is powerful. I think the solution is to add a third dimension to this image. We can just test that. Let's just I'm just gonna go into the debug console and basically run that line. So we've now made a new array, and then I'm gonna try to run this line of code that that I know is going to crash, but now maybe it won't crash and it doesn't crash anymore. So the debug console is very powerful, allows you to kind of experiment with various things and test what should work before you go back and re-edit your code and run everything from scratch again. So I think this will work now. So I'm going to remove this breakpoint that I set. I've saved this new thing. So I'm going to use this restart button to rerun the script from the beginning. Because it's going to rerun everything and hopefully everything will work. No, we got another error. That's okay. This is part of the script. So we run into another error here. So this is saying index 35 is out of bounds for axis 1 with size 35. Okay, so what's going on? Can I run this to go to the debug console? It's my favorite console. You can see that that's a problem. This is fine. You can always, you can see this is like, that works, but indexing J and I doesn't work. So what is J and I? J is 0, I is 35. Okay, so maybe one of these is a problem. Okay, so so I is going from I is now 35 is going up to 105. J is currently 0 and it's supposed to go up to 35. So you can see a new image is 105.35. So those are the numbers we saw. But I should be the first one and J should be the second one. So I think we just swapped these two. And I think that will work. That should work. But I want to demonstrate one more thing, which is conditional breakpoints. So we're trying to stop at I equals 35 and J equals 0. If you imagine we put a breakpoint here and just keep hitting next, we can do that. I'll show you. Let's put a breakpoint here. And we want to stop when it gets to I equals 35. Okay. So we're currently at I equals 0, J equals 0. We can use this new button that I haven't showed, continue. Well, you can step over. This is the slowest way of doing it. That's too slow, right? We can do continue. Continue will basically run until we hit the next breakpoint. So we can keep continuing like this. You can watch J advance over here as we do this. Dun, 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 dun. Very good, right? Okay, this is a little too much. We can edit breakpoints to do what's called conditional breakpoints. Conditional breakpoints allows you to put logic here. So I only want this breakpoint to happen when J equals to 35. And I hit enter. Now I've made a conditional breakpoint. So if I hit continue one more time, nope, my bad. Edit breakpoint. I equals 35. Okay. All right, now I'm going to rerun it and I'm going to hit this and it's going to stop at I equals to 35. Good. So, and basically, so I've set this breakpoint to only activate when I equals 35. So this is a conditional breakpoint. It's very good in for loops when you're like, I'm iterating over hundreds of things that somehow I only crash when when I is like 312. And you don't want to step through this code 312 times. You can set your breakpoint to I equals 312 for it to stop so that you can inspect. Okay, and you can see that if I run it now, it does successfully run. And if I hit continue, you can see that, we're only stopping every time I equals 35 and things are good. Okay, great. So I can remove this breakpoint, remove breakpoint. Do I have my X server running? I think I should. Hopefully this works. All right. So now if I remove everything, this code should run and I should produce a plot at the end. There it is. Awesome. So we created some pixel art. That was the whole point. That was the whole end goal. But the purpose wasn't to show you this. The purpose was just to show you some of the debug tools. So now you see how you can do post-mortem debugging, how you can set breakpoints, how after you set a breakpoint, or you can navigate through your code line by line, going into functions, going out of functions, going from breakpoint to breakpoint. This allows you to navigate through the code and inspect the code at the same time without having to, predict what things you want to print. You can basically look at whatever you want. You can use the debug console to try code to see what should work and what shouldn't work. And hopefully this will help you debug faster. Yes, questions?
Sorry, I don't know if you have more, but.
No.
I was wondering if you could just explain again, please, the purpose of the JSON and how you got, like, after you opened the JSON, how you got to actually doing all this, because I can't figure that out.
No problem. Yeah, so the next step is to you to try it out. What's it? Oh, the question was how did the JSON, after you set up the JSON, how do you get the debugger working? That's going to be the next part. You're going to have an activity, so we'll try to come and help you during that. So maybe wait for that. Right here first.
Then on for every session, or is something by default?
Yeah, it's a good question. So is that configuration file, that JSON thing that we only set once, or how often do I need to make it? You have to make it on a per folder basis. So every time you open up a folder in VS Code, you have to remake that thing. Yeah. Question. Yeah. The question is, does debugging only work on PY files, or does it work on Jupyter notebooks? I think there is a debugger for the Jupyter notebook. I have never tried it. Generally, when I'm in Jupyter Notebook, the cells are self-contained enough that I can debug my way through the cell. Whereas when I'm using VS Code on a bunch of Python files, I'm using it like hundreds, thousands of lines of code where this is really needed. Yeah. Okay. All right. So your activity is to get used to the debugger. We're gonna have you try to understand some unknown code with the debugger. So you're going to debug Orbitize. Orbitize is a package to fit the orbits of planets or other celestial bodies. You don't have to know how to use it. You don't have to know how Keplerian mechanics work. Your only goal is to figure out why is this code crashing. You have an issue that you're tasked to solve. So this is in the debugging markdown file in the day 2 folder. Your task to solve was this issue. I was trying to run this function in Orbitize called calc orbit, and I was running it with some random inputs just for fun. And running it gave me all nans. So I ran this function. It outputs me these 3 variables, and when I print them, they're all nans. The question is, why are they all nans? In particular, your task is to figure out which of the 8 arguments that get passed in is the one that caused it to become nans. That's all you have to do. You don't understand the code. You just understand which of those 8 inputs caused this thing to become nans. So to do this, you'll need to install Orbitize, which hopefully you've done as part of the setup that we forced you to do. Then you'll need to set up the VS Code debugger. The steps I showed you in the demo are also laid out here. So hopefully you step through this line by line, you can get the debugger set up. But this is part of the activity. Part of the activity is just taking the time to get the debugger set up, because it honestly takes time. So it's not a waste of debugging. The debugger is not a waste of the time of the activity. It's part of the activity that we've allocated time for. So follow the steps here. It's the same steps that I just went through in the live demo. And then after you do that, we've helpfully turned that issue on GitHub and Orbitize into an example script. So if you run this script called broken orbitize.py will crash. And your goal is to basically set the debugger here and go into this function and try to understand which of these variables caused the codes to start returning nans. And you'll probably have to go through code line by line. You might have to go into functions, go out of functions, things like that. One last thing. So let's do this. You can do this in your groups and report back on Piazza, or have another post on Piazza. In particular, what line of orbitize do the nans first start appearing? So you have to identify which line of code does the nans first start appearing, and which of the 9 inputs is causing the function to return nan, and report on any modifications you made to make it stop returning nans. Okay, there's a question. The question is, does the debugger work with Jupyter notebooks? Like I said, I don't know. I think there is a debugger for the Jupyter notebook, but I have never used it ever. Just because usually my Jupyter notebook, my file functions aren't very long, so I don't ever use the debuggers for those. Yeah. One more.
Where's the debugger's default if you don't set the current working directory?
The question is, where does the debugger default to when you don't set the current working directory? It defaults to the parent, it defaults to the top level folder that you opened up. So here I've opened up code Astro. The broken orbitize is in code Astro day 2, but the current working directory is just code Astro. But just it's confusing, so I generally recommend you set the current working directory. Okay, so let's break out and work on this. So do this for 25 minutes, and then we'll recap briefly and then do group photos. Okay, so 25 minutes. We'll return at 55 minutes after the hour. All right, let's get back together. Seems like lots of you guys are making good progress. I saw lots of debug environments successfully set up, which is honestly at least half the battle, is getting the right Python environment and the right configuration settings. So nice job, everyone. Hopefully you can take the lessons learned from this workshop to apply it to your own code. So you'll have to set it up again for your own code, but I believe that doing it once, you can do it again. But all right. Let's see what folks get. What line of orbitize do nans first start appearing, and what inputs are causing nans? Looks like a lot of people said negative 99. The mtot equals the negative 99. The last input in the series of arguments is the issue. The negative sign in particular, going from negative 99 to 99, will fix the issue. That's very good. And the issue first appears at line 105 of Kepler.py. Very good. So you guys, for those who are able to do it, that's exactly correct. If you didn't have a chance to do it and want to do it, you can do it this afternoon and see if you can reproduce that same result. But it is indeed that last argument being negative is the thing that's causing the nans, and you could force it to be positive. You can even edit the code. There's like a square root, I think, and yes, there's a square root, and forcing that square root to be positive will make that nan disappear. Good. I just want to close out with a couple last debugging principles that are useful in mind. Ooh, thank you. Thank you for calling. Thank you. We were just going over the answers on Piazza. I was scrolling kind of fast, so I think you guys didn't miss too much on Zoom. All right, I just want to cover a few last debugging principles. These are kind of my own experiences. If you have no idea what's broken, establish islands of sanity. Establish what you believe is correct. That's the first step. And then use process elimination to figure out what could possibly be broken. A good process of elimination is something called binary search. Binary search is often used in programming. Binary search is where you divide, if you have some search space, you divide it in half and search it in one half and then search in the other half. And one way you can do this for debugging is, let's take my whole code. My whole code, something is crashing. I don't know where it is. I'm going to comment out the second half of the code and run it. Does my code still crash? If yes, the bug is in the first half of the code. If not, the bug is in the second half of the code. Okay, and then I'll uncomment another half of the code. Does my code still crash? But you can see how instead of looking line by line, we're doing it. Every time we're doing it, we're dividing the search space by half. And in programming like jargon, we're basically doing an order log n search. So basically, instead of searching, the number of times you have to test and rerun the code to see if it crashes doesn't scale with the number of lines of code. Number of lines of the code, it scales the log of the number of lines of the code. And because of that, you'll search much faster if you have hundreds of lines of code to search through to figure out where the bug is. Googling error messages, especially if they're specific, is very useful. It's actually kind of an art form to know exactly which part of the error message you want to copy. But figuring that out and Googling is obviously very good. Using interactive debuggers like VS Code and like we are just doing for the last hour helps a lot, especially if you have lots of lines of code to sift through, or you're sifting through code that you yourself did not write. That, just it's much easier with a debugger to try to understand how what the code is doing when you can see the operations happening line by line than trying to read someone else's code and understand things. We'll talk about writing tests for your functions later, but writing tests as for your functions can also be used for development. So instead of testing, you might think of it as something you want to make sure your code still works. Testing can also be used for development. Writing a test for your function that says, if I give it this input, I should get this output. And then writing your code after you've written your test. It's called test-driven development, is a way to basically help you figure out exactly, given these, it forces you to write down, given these inputs, expect these outputs, and then you can develop your code to make sure that you are indeed meeting those standards. And debugging is one of those things where practice really helps and experience helps. So just keep at it. As you program more and more, you'll become better and better at debugging. Okay, so that wraps up day 2's lessons. And before we leave, we want to do a group photo. So for folks on Zoom, if you're comfortable turning on your camera, I'm going to do a quick screenshot of everyone on Zoom. So for everyone that's willing, we'll give everyone 10 seconds. Turn on their cameras. We can see people on Zoom that we haven't seen before. So this is great. All right. All right. In 5, I'm gonna take a screenshot and see how this works. 5. I can take screenshots. Okay. We'll fix it in post. Okay, good. All right, one more. Very good. All right, we'll fix it in post. All right, thanks everyone. Good to see everyone's faces on Zoom, and we'll end day 2 here. In person, folks, we're gonna go outside and take a group photo to add to this. All right, thanks everyone.